The absence of a star point grounding on the step-up transformer presents a serious safety hazard. In the event of an insulation fault in the secondary 11,000-volt system, the fault current will not have a defined path to ground. This can result in overvoltages in the 11,000-volt system, erratic operation of protective devices, and the potential for equipment damage and electrical shocks to personnel. The main power system and protection system are arranged for resistance grounding, but the step-up transformer is not properly grounded. This inconsistency can lead to differential protection misoperation, overcurrent protection oversensitivity, and improper fault detection and isolation. It is recommended to ground the star point of the step-up transformer properly, as per the requirements of the resistance grounding system. Calibrate and test the protection system to ensure proper operation with the new grounding arrangement. Conduct a risk assessment to identify any additional hazards resulting from the temporary power supply setup, and implement appropriate mitigation measures. The temporary power supply setup should be reviewed by a qualified electrical engineer to ensure overall safety and compliance with industry standards. Personnel should be trained on the specific grounding arrangements and safe operating procedures for the system. Regular inspections and maintenance should be performed to ensure the grounding system is operating as intended. The current practice of commissioning the offshore platform without proper grounding of the step-up transformer is an unsafe practice that presents significant electrical hazards. Immediate action should be taken to address these concerns by grounding the transformer and implementing appropriate risk mitigation measures. To elaborate further on the safety concerns associated with the lack of neutral grounding, consider the implications for equipment and personnel. Without a properly grounded neutral, the voltage potential of various points within the electrical system can fluctuate unpredictably, especially during fault conditions. This can lead to stress on insulation, premature failure of components, and increased risk of electrical breakdown. Protective devices such as circuit breakers and fuses rely on a predictable fault current path to operate correctly. When the neutral is not grounded, the fault current may be limited or diverted through unintended paths, causing delays or failures in the operation of these devices. This can prolong the duration of a fault, increasing the severity of damage and the risk of injury to personnel. Overvoltages, which can occur due to resonant conditions or transient events, are also a major concern in ungrounded systems. These overvoltages can exceed the insulation rating of equipment, leading to flashovers, arcing, and potentially explosive failures. The risk of electrical shock is significantly higher in ungrounded systems because personnel may come into contact with energized surfaces without realizing the potential difference. A grounded system provides a low impedance path for fault currents, allowing protective devices to quickly clear the fault and minimize the risk of shock. In addition to the general safety concerns, the inconsistency between the resistance grounding of the main power system and the ungrounded step-up transformer can create a number of operational problems. Differential protection, which is used to detect faults within transformers and generators, relies on comparing the currents entering and leaving the protected zone. If the grounding arrangement is not consistent, the differential protection may misoperate, leading to nuisance tripping or failure to detect actual faults. Overcurrent protection, which is used to protect conductors and equipment from overload and short circuits, may also be affected by the grounding arrangement. In an ungrounded system, the fault current may be lower than the pickup setting of the overcurrent relays, causing them to be insensitive to faults. This can result in prolonged overcurrent conditions, leading to overheating and potential damage. Proper fault detection and isolation are essential for maintaining the reliability and safety of the electrical system. Without a properly grounded neutral, it may be difficult to accurately locate and isolate faults, leading to prolonged downtime and increased risk of further damage. The recommended actions to address these safety concerns are crucial for ensuring the safe and reliable operation of the offshore platform. Firstly, grounding the star point of the step-up transformer is essential for providing a defined path for fault currents and minimizing the risk of overvoltages. The grounding connection should be sized and installed in accordance with applicable standards and regulations such as the National Electrical Code Section 250. Secondly, calibrating and testing the protection system is necessary to ensure that it operates correctly with the new grounding arrangement. This should include testing the differential protection, overcurrent protection, and ground fault protection to verify that they are properly coordinated and sensitive to faults. Thirdly, conducting a risk assessment is important for identifying any additional hazards that may result from the temporary power supply setup. This should include evaluating the potential for arc flash, electric shock, and other electrical hazards, and implementing appropriate mitigation measures such as personal protective equipment, lockout/tagout procedures, and safety training. The additional recommendations provided are also important for ensuring the overall safety and reliability of the electrical system. The temporary power supply setup should be reviewed by a qualified electrical engineer to ensure that it meets all applicable safety standards and regulations. This review should include an evaluation of the grounding system, protection system, and overall system design. Personnel should be trained on the specific grounding arrangements and safe operating procedures for the system. This training should include instruction on the hazards of ungrounded systems, the proper use of personal protective equipment, and the procedures for reporting and responding to electrical faults. Regular inspections and maintenance should be performed to ensure that the grounding system is operating as intended. This should include visual inspections of the grounding connections, testing of the ground resistance, and verification of the continuity of the grounding conductors. In conclusion, the current practice of commissioning the offshore platform without proper grounding of the step-up transformer is an unsafe practice that presents significant electrical hazards. Immediate action should be taken to address these concerns by grounding the transformer and implementing appropriate risk mitigation measures. By following the recommendations outlined above, it is possible to create a safer and more reliable electrical system for the offshore platform. It is also important to note that the specific requirements for grounding and protection may vary depending on the applicable standards and regulations. It is essential to consult with qualified electrical engineers and safety professionals to ensure that the electrical system is designed and operated in accordance with all applicable requirements. The grounding system should be designed to limit the voltage to ground on non-current carrying metal parts of equipment. This helps to reduce the risk of electric shock to personnel who may come into contact with these parts. The grounding electrode system should be designed to provide a low impedance path to ground for fault currents. This helps to ensure that protective devices operate quickly and effectively to clear faults. The grounding conductors should be sized to carry the maximum available fault current without overheating. This helps to prevent damage to the grounding system and ensure that it can effectively clear faults. The grounding connections should be made with care to ensure that they are secure and corrosion resistant. This helps to maintain the integrity of the grounding system over time. The protection system should be designed to detect and clear faults quickly and effectively. This helps to minimize the risk of damage to equipment and injury to personnel. The protection system should be coordinated to ensure that the correct protective device operates to clear a fault. This helps to prevent unnecessary outages and ensure that the system remains stable. The protection system should be tested regularly to ensure that it is operating correctly. This helps to identify and correct any problems before they can lead to a serious incident. All personnel who work on or near electrical equipment should be trained on the hazards of electricity and the proper safety procedures. This helps to reduce the risk of electric shock and other electrical injuries. Lockout/tagout procedures should be followed whenever work is being performed on electrical equipment. This helps to prevent accidental energization of equipment and ensure that workers are protected from electrical hazards. Personal protective equipment such as gloves, safety glasses, and arc flash suits should be used whenever there is a risk of exposure to electrical hazards. This helps to protect workers from injury in the event of an electrical incident. Regular inspections should be performed to identify and correct any potential electrical hazards. This helps to prevent accidents and ensure that the electrical system is operating safely. A qualified electrical engineer should be consulted whenever there are any questions or concerns about the electrical system. This helps to ensure that the system is designed, installed, and operated in accordance with all applicable standards and regulations. The temporary power supply should have its grounding system completely separate from the installation's permanent grounding system to avoid any interaction during commissioning. Consider using a ground fault circuit interrupter, or GFCI, on the temporary power supply to provide additional protection against electric shock. Ensure that all electrical equipment is properly labeled and identified. This will help to prevent confusion and ensure that workers are able to operate the equipment safely. Keep all electrical equipment clean and dry. This will help to prevent electrical faults and extend the life of the equipment. Do not overload electrical circuits. This can cause overheating and potentially lead to a fire. Use only approved electrical cords and plugs. This will help to prevent electrical shock and fire. Do not run electrical cords under rugs or furniture. This can damage the cords and create a fire hazard. Do not use electrical equipment near water. This can create a risk of electric shock. If you see any damaged electrical equipment, report it immediately. Do not attempt to repair electrical equipment unless you are qualified to do so. Always follow all safety procedures when working with electrical equipment. By following these safety precautions, you can help to prevent electrical accidents and ensure the safety of yourself and others.